Hello and welcome to our momentum definitions and relationships. Now, just like we broke out in kinematics, we can break all our formulas down into we can categorize them as definitions or relationships. So we've already been introduced to our first definition, which is momentum. And what we know is, in any case, the change in something, the change in momentum, is equal to the instantaneous minus the initial. And that is true when we look at velocity. We can say delta v is v minus v0. Delta x is the change in position is x minus x0, and so on and so on. So we don't really need to have a formal definition for the change in momentum this way, because we can apply it to any quantity at all. The change in any quantity is its final or instantaneous minus initial. Now, the next one is a special case of this, and it's a special case that when the change in momentum is coming about because there is a change in velocity. Because there's a change in velocity. An example of that might be when a car accelerates. The car maintains its same mass, but its velocity changes as it accelerates, so therefore its momentum changes. The other way we can come about having a change in momentum, which we are less likely to see, but we can see nonetheless, occurs when, let's say we have a cart, a moving cart, that becomes filled with rainwater. So it just so happens the way this behaves is that the object will want to preserve its state of motion. It will maintain its momentum, the momentum of the cart that it has. And when rain falls on it, that rain doesn't have any horizontal velocity. But in any case, what happens is that there's a change in the mass, which brings about a change in the momentum. We can also have a change in both the change in the mass and a change in the velocity. And this is the case when we have a rocket. And we're going to look at each one of these cases in greater detail as we go through the course. I'm just giving you an overview of how they might be used. But these four formulas, I could have just written it's delta P equals delta mv. And so really, all we need is P equals mv and this one. And the others then are inferred. If I'm going to change the momentum, I can change the velocity or the mass or both. So we don't really need these three as separate special formulas, but I wanted to point out the different cases. Now, this next formula is we introduce a new variable, J, and that is a new concept. It's called impulse. Now, I will use J throughout the course, but others will use I, a capital I, but I will use J throughout. And then we have F, which stands for force. And then we have net. Now, net for any quantity, so any quantity, let me call it X, X net is the vector sum of any quantity. So, for example, we can have actual positions. So the net position is we might have a +6 position and a -4 position and a +2 and a -1. The net of all of that is 2. That's what we mean by the vector sum. We add up all of them and we end up with 2. Another way of saying the vector sum or the sum of everything is simply to use this Greek letter sigma, which also means sum. So what this says is the sum of all the momentum initially, all of the initial momentum, is equal to the sum of all the final or instantaneous momentum. So at any instant in time, the sum of all the momentum is going to be equal to the sum of all the initial momentum. In other words, the momentum remains constant. Now, what is interesting is this formula seems so small and simple and powerless, but this is a direct statement of the law of conservation of momentum. So this is a big deal, and this we will use frequently as well. So these are our definitions or laws in this case on the left, and we've starred the ones that really matter. In terms of relationships or functions, we see that when it comes to momentum, momentum is equal to the mass times the velocity. Well, velocity might very well depend on time. V equals AT plus V0. V equals AT plus V0. So if we were to take a velocity time graph, and let's say the curve looked like this, well, that's the relationship between velocity and time. But if we took every velocity value and multiplied it by the mass, this would then become a momentum time graph. So a momentum time graph and a velocity time graph will have exactly the same difference. They'll have exactly the same overall shape. They will seem to be indistinguishable from each other. The difference will be is they'll have a different scale. And the velocity graph, multiply the mass, will create the new scale of the momentum. Another way to think about that is we could have two vertical axes. We could have this one, which is scale of velocity, and this one, which is a scale of momentum. And so let's say this goes from 0 to 10, and this goes from 0 to 20. The graph is exactly the same. They just have different vertical axes. And so in this case, we can see the velocity curve, the velocity graph times 2 equals the momentum graph. And so if the velocity is 10, then the mass must be 2. So in the case where mass is 2, the vertical axis for momentum would just be twice as much. But the graph will look exactly the same. Our next set of relationships, if you examine some of the pieces, you'll notice delta P equals M delta V, which we've already met over here. And we've got J equals F net delta T over here, which we met down below. And it turns out, and we're not going to explain why right now, but those two are equal to each other. And that ends up with what I call the four-way equivalence. The four-way equivalence. This last equation is the kinetic energy. Is the energy kinetic. You'll see a lot of other folks say EK. I think that's misguided because we're really talking about energy. We're not talking about some quantity that begins with K. There's all different kinds of energy, and so using KE to me is not a good practice. So in any case, I will always use EK, kinetic energy. Of course, we have mass, we have velocity, and that would give us our kinetic energy. And we will be using this a little at the very tail end of this topic. And of course, we saw in the overview a couple lessons ago that the two big concepts that drive all of motion are momentum and energy. So it shouldn't come as a surprise that this investigation of momentum might connect in at the end with energy. And so this here finishes up our introduction to the definitions and relationships for momentum.